All right, this video is about expected value, and this is how insurance companies determine how much you pay for insurance premiums, and risk is often assessed with expected value. Let me get the ball rolling, and it's starting this way. Suppose you roll 1 6-sided die 6 times and get the following results. So let's take a look at the roll and then the outcome. So let's say here are rolls 2, 3, 4, 5, and 6. And this guy is extremely lucky. He gets exactly those same numbers on the rolls. What was his average roll? Well, what you would do is you would take the outcomes, 1 plus 2 plus 3 plus 4 plus 5 plus 6, and then you would divide by the total number of rolls, which was 6. This equals 21 over 6, or as a decimal, it equals 3.5. So in some way, we want the mean of a 6-sided die to be 3.5. Even though you can't roll that particular number, odds are if you rolled and rolled and rolled a bunch of times, any stretch of outcomes will average around 3.5. So what I'm talking about here are long-term effects. We expect around a 3.5 to be the average roll. Now let me rewrite this in a slightly different manner. So there's our average, or mean. What I'm going to do is break this up in the following way. And then I'm going to add some information here. The first one, I put a 1 in there just for illustration purposes. Second one, so I'm factoring out the numerator from each one of these things. And what you have is you have each outcome, 1. What's the probability that I roll a 1? Well, it's 1/6. A 2. What's the probability that I roll a 2? It also happens to be 1/6. If the die is what they call fair, the probability of rolling any number is always 1/6. So there's outcome 3, rolling the number 3 times 1/6. I do this for all the outcomes. So the form that it takes looks like this. Remember that symbol for summation? I have x, and then I have the probability that x occurs. So I add up all of those. So here is the x is 1 in this case, and the probability that you get a 1 is 1/6. Then I add to the next. 2. What's the probability of getting a 2? Well, it's also 1/6. And I run them all through all the possible outcomes. So what we come across is something called expected value. So in this, let S be a sample space. Define, I want to be careful here. S be a sample space. When I'm talking about a sample space here, I should make sure to say that it's numerical. The outcomes all have to be made sure that they are numbers. That way I can work, that way I'll be able to actually do multiplication. So they have to be numbers. Define the expected value as e with x in parentheses will equal the sum of x times p of x, where x ranges through all the values in S. Let me show you how this works in a little more detail. Expected value, you should think of it as the results that you should get, not necessarily the results you do get, but what should happen. Flip a coin over and over again. What I'm going to do is do the expected value for each of these. So let's do flip one time. If I do that, my sample space consists of only two outcomes, heads or tails. Now, when I do the expected value of this, it looks like this. Now, you cannot do this. I cannot do h times p of h plus t times p of t, because h and t are letters. I need them to actually be numbers. So I need a number to occur for h, and I need a number to occur for t. And I also must be more specific on my expectation. So let's do it this way. I'm going to cancel this. What are the expected number of heads? Be grammatically correct. All right, so now what I can do is when I do my e of x, I can do what's the probability of 0 heads? And then I can do what's the probability of 1 head? So instead of 1h, I'll just put a 1, and I'll just put a p of 0 so it'll work. This way we've created them they're numerical. Now, the probability of 0 heads is 1/2. You can get tail, and the probability of getting a tail is 1/2. The probability of getting 1 head, of course, is 1/2. And we get 1/2. Let me do another one. Let's flip 2 times. This time, it looks like this for our sample space. For 2 times, we could have 2 heads. We could have a head and a tail. We could have a tail head or tail tail. So now, what I'm going to do here is x equals 0, x equals 1, x equals 1, x equals 2 for the number of heads. So what is the expected number of heads? So the expected is 0. 0 heads, what's the probability of 0 heads? Plus 1 heads times the probability of 1 heads, plus 2 heads times the probability of 2 heads. So let's take a look. The probability of 0 heads, that means all tails, is 1 out of 4. The probability of 1 head, I've got 2 situations that have 1 head out of 4, so it's 2 out of 4. The probability of exactly 2 heads is 1/4. Notice it's nice, they all have the same denominator of 4, so I can add 2 plus 2, and that will be 4/4. So if you flip a coin twice, you would expect 1 heads. Let's flip 3 times. Here S equals, we can have 3 heads, or we can have 2 heads. We could have 1 head, or no heads. So what is the expected number of heads? So we'll do as we did before, 0 heads times the probability of 0 heads, 1 head times the probability of 1 head, 2 heads times the probability of 2 heads, 3 heads times the probability of 3 heads. The probability of no heads only occurs here when we have all tails. That's 1 out of 8. And then the probability of 1 head, how many of those? We've got, over here I see 3 of them. So that's 3 over 8. 2 times the probability of 2 heads, and that's 1, 2, 3, these 3 right here. So that's also 3/8, plus 3 times the probability of 3 heads. That only happens in 1 out of 8 places. Once again, common denominator of 8, I have 3 plus 6 plus 3. So that is a total of 3 plus 6 is 9. So that's 12 over 8. That equals 1.5. So if you flip a coin 3 times, you'd expect to get 1.5. Well, I hope you can see a pattern here. Flip 4 times, and the expected number of heads is 2. So really, what we're getting here is we're just taking the number of flips and dividing by 2. So the expected number of heads if you flip n times is n over 2. Now, notice that it makes sense when I have an even number for the number of flips, but the odd number of flips is a little bit weird, but mathematically it still makes sense. Additionally, when you look at what I just talked about, I could have said tails throughout the whole problem and gotten exactly the same numbers, because whatever happens to heads is mirrored by whatever happens to tails. You purchase a 5-year term life insurance policy that pays $100,000 if you die. The actuaries determine that your risk of death during any time in those 5 years is 0.000003. That's 5 zeros. So that's how much they've determined. The premium is $300 per year. What is the expected value for the insurance company? All right, for this problem, since we're talking about the expected value for the insurance company, this is how much money they expect to make on you. So long as you survive the 5 years or any portion of the 5 years, they have formulas to determine how much money they made from you. Let's take a look at how this works. I'm going to put here for you, let's say the year of death. Now, you bought a 5-year policy, so we have the first, second, third, fourth, and fifth. So for each of these, we have to think of an outcome for the insurance company. This outcomes will be our X values, if you will. So let's take a look. If you die during the first year, they have to pay out $100,000, but at the beginning of the year, they collected the premium of $300. So at least they got that going. If you die any time during the second year, they have to still pay out the $100,000, but this time they were able to collect 2 years worth of premiums from you. Next, the same thing for 3 years. Hopefully you can see the pattern here. And then if you live to make it to year 6, which would be the end of the policy, after the policy's over, all they did was make $1,500 off of you and they didn't have to pay out. So now when we do our expected value, the X values are a bit weird now because the X values are going to be money. That's what the insurance company is interested in. So these, if you will, these are the X values up here. So the first one there was negative $99,700. So negative $99,700 times the probability that you will die in the first year. The next one, 99,000. This time I have to do negative 100,000 plus 600. So that's negative 99,400 times the probability you'll die in the second year. Minus 99,100 times the probability that you'll die in the third year. Minus 98,800 times the probability you die in the fourth year. Minus $99,400 times the probability that you die in the fifth year. And finally, plus 1,500 times the probability that you live longer than 5 years, so that you die. They really don't care if you die in the 6th year. That's all that matters, is that they survived the policy and they made the most amount of money. Now, I am using for this the same probability every single time. So I'm assuming that you have one probability of death for the entire 5 years. I'm not absolutely certain that term life insurance works that way, but I think it's pretty close. So let's take a look then. I have to take each of these numbers, 99,700, and multiply it times that probability, 0.000003. And you got to go through all the outcomes. Now, the probability that you won't die during this time is 1 minus 0.000003. Now we'll just run these through the calculator. I'm going to do a little bit of simplifying though. You notice the 0.003, well, 5 zeros and a 3, was multiplied to all those negative numbers. So I'm going to go ahead and strip it out. And then don't forget to add the end part, 1500 times 1 minus 0.000003. And let's see how much money they think they're going to make off of you. So I have my 0.000003. Let me start a parenthesis. And you know what? I'm going to save myself a little more time too. All of those numbers are negative. I see that. So what I'm going to do instead is I'm going to insert in front of this whole piece my negative, and then I'll just put positive numbers inside of the parentheses. Now let's add them up. So I got my 99,700. I gotta put my cursor where the plus is. Then we have 99,400, 99,100, 98,800, 98,500. Finish the parenthesis off. Plus 1,500. Start a new parenthesis. 1 minus 0.000003. Finish the parenthesis up. Got to be careful there. Finish that parenthesis, and let's see what we have. It did not like something I wrote. Let's change that to a real minus. And it looks like I have 1498.51. So in their version of you, they intend to make $1,498.51 on average from you. Now imagine having millions of customers. You can see where this adds up quickly. And because in general they're going to make a ton of money from each of their policyholders, when somebody does die, they have more than enough money to pay out, say $100,000 or $200,000, because these premiums are accumulating in the millions, maybe even in the billions every month. What is your expected value if you buy one Mega Millions ticket when the jackpot is $1 million? I know this thing gets a lot bigger than that. In fact, I'll tell you what, I'm going to change it right on the spot. We're going to change it to $10 million. Well, there's really only two outcomes here. You either win or you lose. So let's take a look at what winning does for us and then what losing does for us. If you win, you get $10 million. And you know what we could probably do? I think it's not a bad idea. Let me get rid of that part of it. But let me get, you win $10 million. However, you did spend $1 on the ticket. Now, if you lose, you're simply out $1. What are the probabilities that these happen? Well, if you remember, the Mega Millions you You got 47 numbers, and you pick 6. So the probability that you win since you only bought one ticket, it's 1 out of 47C6. So let's take a look at your expected value then. Now, if you win, you do win $10 million. Well, let me first write down the formula, even though it won't look like the formula. I'm going to make it look like the formula in just a second. One outcome is that you win. That means you get $10 million minus $1 times the probability of winning plus -1 times the probability of losing. So we have 9,999,999 times, I'm going to take this parenthesis out, the probability of winning then is 1 over 47C6. Then we have minus the probability of losing is 1 minus 1 over 47C6. And let's go ahead and calculate this number. So I got my, how many 9s do I have? 7 of them. 1, 2, 3, 4, 5, 6, 7 times, or you know what, I can just do divide, because that really is divided by 47C6. I feel uncomfortable not putting in parentheses, so I'm going to do that. Let me start it with my 47. Remember to go into Math, PRB, and then choose number 3. And then we want to put 6 because we're choosing 6 of them. Finish off that parenthesis. And then I'll do minus in parentheses now 1 minus 1 divided by, same deal, I'm going to put it in parentheses, 47, math, number 3, 6, finish that parenthesis. Now I also had a parenthesis here in front of this one, so I need to put this parenthesis here that's after the 1 over 47C6. And enter. So we see about negative 0.07. We'll convert it to dollars and cents. So on average, you expect to lose about 7 cents every time you play the lottery. Let's write this, -7. One way to write 7 cents is this way. Another way to write -7 cents is just this, and then put the symbol. So either one of those is a correct way of writing the answer. So what that means, though, is the lottery is making a little bit of money on you on average. Now imagine millions and millions of people are playing, and they are making a little bit of money from each of these players. Now the more tickets you buy, the more money they're going to make. You simply multiply these numbers. Additionally, your expected value being -7 cents means the lottery commission's expected value is plus 7 cents. So everything, if it's negative for you, it's positive for them.